So the next part of the video, we're going to talk about Euler's formula and the different ways we can write a complex number. For example, we've got an exponential form right here, we've got a mod arg form, and the third one is a Cartesian form, which we already know is x plus iy. So that's a Cartesian form of a complex number. This right here is very related to this. So mod arg form is basically, we can write it as r, which is the modulus. We've got cos theta plus I sine theta. So that is basically mod arg form. So the value of r can be, we can get it by, if we draw up a complex plane, we've got imaginary, we've got real. So let's just say this is a complex number z. We know that this value from there to there, so that value there is its real component, which is going to be cos theta, and that value from there to there is its imaginary part, so it runs down the imaginary plane. So that is its I sine theta. So this basically is like Pythagoras. So this value right there, value of r, is determined by Pythagoras. So basically x squared plus y squared, so x squared plus y squared square root is basically the value of r. So that's how you get the value of r. Argument, this theta, these two values always remain the same. So the theta for this and that are always the same, they never change. And that's basically easy trigonometry. We put that's the theta there. And then you just go tan, sorry, this is not squared, this is just x and y. We go tan of y upon x. That's how you find the theta. So that's the mod arg form, and then the exponential form is basically the same thing. So e to the I theta is equal to this. So e to the I theta is basically equal to that. So that's how you get r e to the I theta. So yeah, just a little bit of theory stuff. So now we'll get on to the examples. We got this out. So we've got an example right here. It says z equals to root 3 plus I. So we're going to write that in this form. It's exponential form. So we've got z. Let's just quickly draw up z. So z is root 3 plus I. In a complex plane, let's put that in. Root 3, so this is all positive, so it's all going to be in this quadrant right here, the first quadrant. So theta is always going to be positive in this case, or in the first quadrant. So root 3, somewhere around here, 1, just push up. So this complex number is somewhere like this. That's the complex number there. So, again, mod arg form, modulus, we go x is, so modulus of z, we write that in this, so the absolute value of z, so that's how you write modulus. We go square root of bracket root 3 all squared plus 1 squared, which gives me root 3 plus 1, which equals to 4. Square root, which is equal to 2. Plus minus 2, but in this case it's an absolute value, so the case is always going to be positive. So 2 is the final answer. So that's your value of r. R we know is 2. Theta, we can figure out theta now, right there. We know 1 upon root 3. We can go tan inverse, or arctan some people like to say. 1 upon root 3. And the value of that then gives me, you can put it in calculator if you want. Minus tan of 1 upon root 3. That then gives me 30 degrees. So they usually like it in radians, so 30 degrees is pi on 6. So theta then equals to pi upon 6. So your final answer for A, writing in exponential form, would be 2 e to the I pi on 6. So that's your final answer for this example right here, A. Now we can go on to question B, which is power of complex numbers. It's another key aspect to look at. So we've got that for A. Now we can come back to B, which is going to be z to the power of 4. So if z equals to that, so if z equals to 2e I pi on 6, 2e to the I pi on 6, z to the power of 4 is going to be equal to brackets 2e to the I pi on 6 to the power of 4. To the power of 4, we have 2 to the power of 4, 2 times 2 is 4 times 2 is 8 times 2 is 16. You get 16 e to the I 4 pi on 6. So that's your answer for that. We've got to be careful here though, because the argument of a complex number is defined between negative pi not inclusive arg of z less than or equal to, so sorry, negative pi less than arg of z less than or equal to pi. So this is the principal argument. It is only defined as negative pi and pi, the argument of a complex number. And the reason for this is, again, we draw it up. This is, we can say 0 degrees, and you can say this is pi degrees. So in a complex number, it only goes like that, pi, or like that, pi. If it's out of the principal argument, for example, let's just say this was, in any case, to the power of 24. Let's just say z to the power of 24. For in that case, this would be 2 to the power of 24. We get some number, so 2 to the power of 24. We get some extreme level number, but if we're talking about the argument, we go I 24 pi upon 6. 6, 1, 6. So we get 4 pi. I equals to 4 pi. If you get that, that's not your final answer, because that is out of the principal argument. So you minus 2 pi from that, because 2 pi, so let's just say if that's 4 pi, if you minus one full circle, you come back to 2 pi. You minus another 2 pi, you come back to 0. So you just put that as 0. So your argument is a 0. Just comes back to there. So whether you're behind this or in front of that, you always minus or add 2 pi to come back into principal argument. So yeah, that was just for this first one. The next one is we find z to the square root of z. So we've got z is 2e to the I pi on 6. We go square root of z is square root of that, which is 2e to the I pi on 6 to the power of half. To the power of half. That to the power of half is just root 2 multiply I pi on 12. That's your final answer for this example right here. Alright, for this next example, this is an exam style question that they gave us. It says, show 1 minus root 3i to the power of 9 is purely real. So this question right here, it kind of sums up all the stuff that we've learned today. So yeah, let's just get straight into it. So we've got 1 minus root 3i. One thing I really like doing, especially in an exam, is like knowing where the complex number is, so I'm not confused with anything. So we've got 1, which is real, somewhere around here. Minus root 3 would be down here. Root 3, just around there. So that's the complex number, z. I like drawing like a little triangle just to get my head around the Pythagoras stuff that we're going to do. So 1 is over here, root 3, minus root 3, my bad. So 1 minus root 3. So straight away we're going to try and find the modulus and argument of this and convert that into exponential form. So we've gotten, so straight away we can go modulus of that would then be 1 squared plus square root of minus root 3 all squared. Doesn't really matter, looking on the square root of 4, which is 2. So the modulus of this is going to be 2. Always write that down. So we've got 2 e to the I. Now we know the argument. 1 upon, tan theta. So we know this is theta in this case is going to be negative. It's in the fourth quadrant. Tan theta, inverse tan theta, sorry, minus root 3 upon 1. What do I get? Minus root 3 upon 1. We go inverse tan of minus root 3 upon 1, which is just minus root 3. We get negative pi on 3. 60 degree, negative 60 degrees, so negative pi on 3. Now, that is the argument right there, negative pi on 3. Okay, another thing I like checking is I always put in cos negative pi on 3. See what you get. Cos negative 60. You get a positive number, so that means your argument is correct. It's in the principal argument, and you're using the right answer. So we get negative pi on 3. Sub that in, we go minus I pi on 3. Minus I pi on 3. That is your number of z to the power of 9. Now that we know it's to the power of 9, this is where the tricky part comes. Show that it's purely real. 2 to the power of 9. What is 2 to the power of 9? 2 to the power of 9, 2 to the power of 9 gives me 512. So we have 512 e to the negative I, 9 upon 3 is 3 pi. This is what I was talking about earlier in the video, in the earlier videos, where this is out of the principal argument. This is out of the, now we minus from 3 pi, we minus, oh, it's negative 3 pi, right? We add 2 pi to that. So we get negative pi. We're getting negative pi here. So theta is then negative pi. So 512 e to the negative I pi. E to the negative I pi, right? What is the answer to this? So we can change this back into mod arc form because it's asking us to show it's purely real. Mod arc form, we go 512 brackets cos negative pi plus I sine negative pi. What do you get for sine negative 180? You get 0. So that then is just cancels out. So that then cancels out. Because sine 180 is 0, so sine negative 180 is also going to be 0. So that then cancels out. So this then leaves us with 512 cos negative pi, which is negative 512. Final answer. Sorry. Yeah, that's right. No, that's right. Negative 512. So that is how you do this question where we used a mix of all the stuff that we've learned today.